And again?
Yes, we are.
Okay, then welcome back to the second part of the masterclass today, to the second session. I think since we took a little bit longer, as said before, we will wait 2 more minutes that everybody can dial in, and then we will continue with noise and vibration signal processing at the end of line test. Yes, and also Timon, if there are some more questions, we will also handle them at the end of the session.
Right, great.
Okay. Do we have some more questions just to left over some time?
We have some left from the last session, yes.
Okay.
But I think we put them after the presentation. But
Yes, that makes sense
yes,
to
okay.
put them to the end, of course. So I think.
You think we should get started here, Olaf?
Yes, good idea.
Okay. Hello, everybody. Welcome back for those who are in the last couple sessions here, and welcome to anybody who's new. So in the last session, we covered the test bench considerations for noise and vibration part of testing. Obviously, our industrial quality testing uses those techniques to identify defects. So in this session, we are going to take a deeper dive into how we process those signals and things that are important in respect to that processing. So I did want to mention that we are going to send this presentation out and the recording next week, and that will be ready next week. Everybody should get an email. If you don't, feel free to reach out to us. And with that, I'm going to hand it over to Olaf. Olaf is, again, one of our industrial quality testing experts, and we've been the company for Innovus has been doing this for 20 to 30 years. So you're in good hands with Olaf here. So Olaf, you go ahead and take it away.
Yes, thank you, Frank. Then we continue as always with the agenda. Some slides to recap about the last sessions for those who are new today. Then we will talk about the basics of signal processing. That's at first the goal. What does signal processing? What is it good for? Then a very important thing, if we want to understand why to use a certain method, is to understand the signal types and how they behave in these signal processing functions. And then we explain our typical way to drill down the signal analysis, or to how we use the signal analysis as a kind of drill down to develop the system from the signal to the metric. Since at the end we are interested in the metric that tells us if our device is good or bad, or if our device under test has a certain defect. And we will show how we come from the signal to this metric. There we talk about angle synchronous analysis. This is part of this slide 12 from the last presentation. Maybe some of the slides in this presentation answer most of the questions. Then we will talk about enhanced analysis methods, and at the end at the techniques that we use to define metrics. So let's start with what happens up to now. I keep it short since the time between the sessions are not so long as it was planned at the beginning. By the way, I made the same sessions for Europe, and there we had 2 sessions a week, so this was more important. Yes, we are talking about the measurement chain from sensors to the hardware, which digitalizes the signals, and then we do digital signal processing in our application. That's the main topic of this session. And the last session dealt about test bench integration, how to communicate with the Novus system, how to integrate it in the test bench from the mechanical and the electrical and the software point of view. Yes, but today in this session we will talk about analysis and classification. In the last session we spoke a little bit about it, why this is why this is necessary. What is the you may think I do not do this if I measure temperature or if I measure a diameter of an or geometric measure of a certain part. So why do I have to do this for noise and vibration? It's necessary because we always get a mixture from different noise sources, not only from the device under test, but also from the test bench drive, from the test bench, from the environment. You remember the example with the crowd. We only want to listen to this one person in the cloud that has the important information for me. And in our case, this is maybe one certain tooth mesh that has the information for us if the tooth flank is damaged or not. That's what we are interested in. And to filter this out, we use digital signal processing. And to understand this a little bit better, we start at the basics. So the question is, what is the main goal? Why are we doing signal processing? Because the signals are always a mixture of components. Some of them are disturbances, some of them are of interest. And the main task is suppress all the signal components that are not coming from the device under test, that are disturbances, external disturbances, internal disturbances from the test bench. And in the second step, separate the signal components from the device under test, depending from their sources. This is quite important for end-of-line testing, especially of quite complex devices under test, as we have it, for example, if you look at IC engines. An engine consists of several parts, some 100 parts, and there are a lot of possibilities of faults in an IC engine. And as I mentioned in the first session, it does not make sense to only say this engine is not okay. We have to identify a fault. And to be able to identify a fault, we have to separate the signal components coming from the single mechanical components. From the, sorry, my headphone is disconnecting. Sorry for that. I will fix it until tomorrow. Yes, and to separate these components depending from the mechanical components, depending from the issues that may occur, is an important step towards a metric. A metric that validates the signal components and that helps us to identify an issue. So that's more or less also the drill down, suppressing of disturbing signals, separating of the interesting signals, definition of metrics about the signals. Now the question is, how do we do it? The general idea is to find the criterion to separate signal components. Since we do not have any extra information about the signals, we only have our ear. If you think about this restaurant where you listen to that one person in the cloud, then you also see your eyes. But if you go, okay, now it's not possible everywhere in the world. If you would go to a restaurant and close your eyes and try to concentrate on one voice in the restaurant, it's quite not so easy. And doing that, we need to find the criterion. For the voice, we could try to find out, is it a high frequency voice, a low frequency voice, and then we can try to concentrate on it. For our devices under test, we have to find out what signal components are emitted, what kind of signal is emitted, and can we use the special characteristics of this kind of signal to filter it out from all the other signals. A very easy thing would, for example, be using really a filter that Sorry for the disturbance. I used another port now. I hope it is better now. Yes, the easiest way to do such a separation would be a filter and frequency range. For example, if you are looking only at the signal component that has a frequency of 1 kilohertz, then we can build a filter that filters out this 1 kilohertz, and we can assess the level of this frequency. That's quite easy, but in most of the cases, it's not so easy. The criterions are a little bit more complicated, and therefore also the signal processing methods are not so easy. Yes, and therefore we have to find the right analysis, then set it up in a way, set the parameters in the right way that it uses the criterion. And then we use the output of this analysis for defining the metrics. That's the way how we do it. Here's a kind of motivation how it could look like if we have only the raw signal. In our cases, we have two different signals. We see it's a mixture. No fault identification is possible since both of the signals look quite similar. I'm not able to define any kind of metric here in this picture that helps me to distinguish between the upper and the lower picture. But doing the right analysis function, in our case, a simple spectral analysis, we are able to separate the components of these signals. In our case, we have noise. That is something that you can see here on the floor. Here also, and then we have two peaks in the spectrum. That means we have two harmonic frequencies. In that case, and if you look at the second example, we only have one of these harmonics. So looking at this picture, it's quite easy to distinguish between those two examples by defining the right metric. In our case, an assessment window that assesses the level of this single frequency line. So that's what I meant in using analysis functions to separate the signal components from each other. In our cases, we assume that the noise is the disturbing signal that we have in the sensor. That is a mixture of all the environmental vibrations or noises that we have. And then those two harmonic components are the components from the device under test that we use for assessment. And in that case, the assessment is quite easy. That means, as you see here, the function that we use, in our case, the analysis function, uses characteristics of the signals. And depending from the characteristics of the signals, we have to find the right analysis function. And to be able to do this, we have to understand the characteristics of a signal. For example, we could do this in time domain and frequency domain. That's what you have seen in the picture here. On the left side, we are in time domain. That means on the x-axis we have seconds, and on the right side we are on frequency domain. On the x-axis we have hertz, the measure, the unit for the frequency. And here is the same, a little bit more theoretically. This is time domain. We have here a sinus wave. The picture shows on the x-axis the time, on the y-axis the amplitude of the signal of this vibration. And then I can do, for example, a spectral analysis, for example, by using an FFT. And the result is a so-called spectrum. That means now I've done a transformation of the signal. It's only a kind of calculation. It doesn't change any information of the signal. It only represents the information in a different way. Here in this picture, I can see a sinus wave with an amplitude and with a time span for one period of the sinus wave. And if I look in spectral analysis, the sinus wave represents as one line. All the other lines are 0 in the spectrum. And the position of the line is the frequency, which is 1 divided by time of the period. So that's quite easy. We can take this characteristic of this analysis function to separate signals from each other. For example, if we have on the left side a mixture of several of these sinus waves, then we can use the spectral analysis to separate them to different lines and to assess them separately from each other. That's the advantage for this kind of signal, for example. So to understand how we could separate them, it would make sense to have a look at several kinds of signals, how they behave in time domain or in frequency domain. Or we can wait a little bit with that, and we can also have a look at another pair of domains that's quite important for rotating machinery. I already mentioned that in rotating machinery, many of these frequencies that we see here are depending from the revolution speed of the device under test. And therefore, we try to normalize this by the speed, and that's what we are calling order. That means if we are moving in angle and order domain, then our x-axis is not time, but it is angle of a reference shaft. And if we do a spectral analysis of this kind of signal, then we get a so-called order spectrum in order domain. From angle domain, we switch over to order domain. And the x-axis on this plot is now not frequency, but it is order. And the order has no unit, since it is calculated in a way revolution frequency in hertz divided by frequency on the reference shaft, also in hertz, and hertz divided by hertz is 1, and so we do not have a unit here. But the relation is quite similar. The time span of this period of our sinus function is n times 360 degrees. That means 1 revolution of our reference shaft. And order is 360 degrees divided by this time, and then we get an order. And so it's quite easy to understand. If I have 1 vibration period per revolution of the shaft, then I have order 1. If I have 2 periods, that means if this n is 2, then I have order 2, and so on. And this is the way how the orders are calculated. And then we can use this also as a kind of transformation, depending if we have rotating machinery or if we have something that has a fixed frequency. So now let's have a look at this for several kinds of signals. The first one we already have seen, it's a so-called harmonic signal. The harmonic signal has a quite typical characteristic. The shape of the curve is a sinus wave. That's quite easy. It's completely determined. It can be calculated by the sinus function. We have such signals in practice. For example, an unbalance of a shaft typically is a sinus wave, or is represented as a sinus wave. So in frequency domain, we already learned we have 1 peak. The position of the peak is the frequency. As more right the peak is, as high as the frequency. Peak on the left side has a low frequency, and the level corresponds with the amplitude. Then the second type of signal that we want to have a look at is a so-called periodic signal. This could be a noise emitted by an oil pump or by a compression of an IC engine or by any other recurring movement in our device under test. And here we see that we have a certain shape of the signal, but the shape is different to a sinus wave. A sinus is called harmonic signal. A periodic signal is something that has a deterministic shape. That means it can be calculated by or described by a formula, but the shape is not a sinus wave. It has a different shape as you see it here. And if you look at this in frequency domain, you do not see only 1 line. We see several lines in the spectrum, and these lines are called harmonics. That's quite a little bit inconvenient, since a signal that is called harmonic signal does not have harmonics, but in periodic signal has harmonics. I'm sorry about this, but this is how my professor has taught it to me and how it is specified in literature. So that means if you have a periodic signal, we can assume that this kind of signal is a mixture of several harmonic signals with fixed frequency relation to each other. That means an harmonic is always twice, 3 times, 4 times, 5 times, 6 times the basic frequency of the harmonic of the periodic signal. That means every periodic signal has a basic frequency that's more or less 1 divided by the time of one period of the signal, and then it has harmonics. So if you look at the spectrum, for example, it could also be an order spectrum, and you see one certain line, then you should have a look at the frequency that is twice the frequency of the line or 3 times the frequency of the line. And if you see also a contribution there with a high probability, these lines have only one origin, which is a periodic signal. This could be, as I already mentioned, an oil pump that we see on several orders with some harmonics. And if we let's have a look at this at such an oil pump signal, for example, then if we see differences in the levels of the harmonics, then this corresponds with a different shape of the signal. So if you have a certain fault that the oil pump does not work in the way as we expected, then the vibration or the forces in the oil pump change, also the vibrations change, and this can be analyzed by different levels of the harmonic frequencies. The position will always be the same. It is always exactly twice, 3 times the basic frequency, but the level can change. So that's quite easy. Every line is a tone in these pictures. High peak corresponds with high amplitude, and the tone becomes higher if the line moves to the right. And therefore, also some examples may be interesting. You can take a signal generator and generate tones with different frequencies to get a feeling, to get an impression. What does it mean if I have a 1 kilohertz tone, a 2 kilohertz tone, a 200 hertz tone? How does it sound like? This sometimes helps also to analyze faults, to understand faults if we have a kind of impression about what we are seeing in the spectrum. And so some examples could help. And the next class of signals become a little bit more complicated. The modulated signal, if you remember the second session where we talked about this gear mesh behavior, there we have seen that if the tooth gear is not completely, if not every tooth is completely exactly the same than the other tooth and tooth gear, then we have modulation. That means modulated signals typically occur if we talk about gear meshes, about timing drives, timing belts, timing chains, all these stuff. And there we usually have modulated signals. In frequency domain, we see the basic frequency, or we call this also carrier frequency. In frequency domain, this is the center frequency, which represents the behavior of this high frequency signal, what you see here. It can be a sinus signal, then you have only one peak in frequency domain, but this signal, which is modulated, also can be a periodic signal. Then you have also harmonics. That means you do not only see one line of the carrier frequency, you see twice the carrier frequency, 3 times, 4 times, and so on. And the frequency that is modulated on this carrier is shown as sideband lines. This is a kind of FFT rule. What we are doing here is an FFT spectrum. And a mathematical rule is if we do a multiplication in one domain, that means in our case in time domain, then this leads to a convolution in frequency domain. The modulation is a multiplication. I multiply the carrier with the modulation signal, then I get this typical shape. And this modulation, this multiplication leads to a convolution. And if I have lines in the spectrum, then convolution means I can solve this convolution integral. I have a lot of zeros in this integral if I talk about harmonic and periodic signals. And at the end, it looks like as the modulated signal is shifted around the carrier. And so the distance of this line from the carrier shows the frequency of this modulation. If I have a high frequency here, many changes over in a short time, then the sideband lines are far away from the carrier. If I have a very slow moving characteristic, then the lines are quite near to the carrier frequency. And interesting, especially if we not talk about time and frequency domain, but about order domain, is that also these lines are on dedicated orders. If I have an effect that is synchronous, or if you think about this tooth mesh again, if I have an effect that is synchronous to one tooth gear, then I only have lines with a distance that correspond with the transmission ratio of this tooth gear. And so I can also separate the effects from different tooth gears. And this is also true for electric motors, for belt drives, for chain drives, for all other things that behave similar. So modulation analysis is quite important if we talk about all these gear mesh timing stuff. And it's the basic function that we need to analyze these components. Then the next class is noise. This is most of the time it's the main part of our signal. If you look at the raw time signal, it looks like noise always. That means you will probably never see such sinus waves, such modulations in really in time domain. If you look at the raw signal, most of the time you see something like this. But here also frequency domain has a real big advantage that this noise will be transformed to a kind of noise floor. And the noise floor usually, or hopefully in most of the cases, is much lower than the harmonics that we are interested in. So that shows also the importance to have a good noise shielding from the environment, or to take care about noise or noise of the sensor, noise of the acquisition unit. Since if the noise is too high, then it will cover these small frequency peaks, and we will not be able to measure or to assess small deviations from at the gear mesh, for example. For example, this you remember this picture is from the elliptic gear. If the elliptic is quite strong, then we have really loud sideband lines. If it's quite only a very small elliptic shape of the gear, then these sideband lines have a quite low level. And if the noise is higher than the level, we do not see them, and we cannot assess the elliptic behavior. So noise floor is always interesting. In general, we can say the modulated signals, the information about, if you talk about modulated signals, the information about, or let's say most of the quality information is concentrated in the sideband lines. If you look at tooth gears, a good quality tooth gear is homogeneous. Every tooth looks like the other. If they are different from each other, then it's a quality criterion. Then the quality is not so good. And we see this effect in the sideband lines. That means at the end, if you look at gear mesh, then the sideband lines are quite more important than the gear mesh frequency itself. And to parameterize the analysis in a way that we are able to see these sideband lines is quite important to detect faults. Yes, in the noise floor, it depends. It represents the surrounding noise, and the height of the noise floor is also depending from the resolution of the spectrum. If I have only a very small resolution, then the noise floor is higher. That means the noise is concentrated on some FFT bins. And if I increase the number of FFT lines, the energy of the noise is spreaded to all these lines. And so the noise floor goes down. It has a statistical reason, and we have to talk about spectral densities and all these things to understand this more deeply, but time is running. It would be too much to explain this theory behind this in this short webinar. But we have to take and keep in mind, if we use a high resolution spectrum, then the noise floor goes down and it helps us to detect smaller defects. Then the next class of signals are transient signals. That means peaks. One clap, for example, is a transient signal. If we look at a device under test, then this could be an external hit on the test bench, or forklifter puts a pallet on the ground very heavily, then transient occurs, and this transient excites frequencies of the device under test. And what we see in frequency domain is more or less the frequency response of the device under test. At the end, one transient, to detect one transient as a fault is quite not so easy, because many external noises are transients. That's why we try to suppress single transients. But it's different if we talk about periodic transients. They could, for example, occur if I have a tooth damage. If one tooth of my tooth gear is damaged, every time it is meshing, it makes tick. And then if the tooth gear rotates, it makes tick, 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 tick. And the distance between the ticks is determined by the number of teeth and by the revolution speed. And if I know both of them, then I can extract these peaks from the surrounding signal too. And this is better possible in time domain, since in time domain the energy, or in angle domain, the energy is concentrated on a few peaks. If I transform this in frequency domain, then I see the resonance behavior of the device under test again, but I also see many, many lines. This is another FFT rule. If I have a series of transients in time domain, I will also see a series of transients in frequency domain, where the distance is one divided the distance in time domain. That means if I have a few peaks in time domain, I have a lot of peaks in frequency domain, and vice versa. And so it doesn't make sense to use frequency analysis to analyze such peaks. To analyze them in time domain or in angle domain is much more convenient. That means pulse series in time domain lead to pulse series in frequency domain, and they can help us to identify defects in our device under test. Yes, here we were talking mainly about time domain, but what about this order domain again? Here again, this picture you remember, maybe you remember this picture from yesterday. We have seen in we had a look at the signal components that are emitted by an eDrive during the test. We have a lot of angle synchronous orders or angle synchronous components here that are unbalanced, alignment, bearing damages, tooth damage, tooth length, shape, rotor eccentricity, deviations of the magnetic fields. All these things can be found if you look at the shaft orders, the gear orders, and the engine orders. And these orders are dependent, the frequencies of these signal components are depending from the speed. And so some synchronization would make sense. That's the point where angle synchronous signal processing is used. It is done in a way today that we use, that we assess the vibration of our device under test, and we take one shaft most of the time, so many shafts, and acquire a tacho signal. And by using this tacho signal, we can resample the signal, the vibration signal that we have acquired with a constant sample frequency, and can generate a signal that has an angle synchronous, an angle equidistant sample rate. And that means we move away from the time and frequency domain to an order and angle domain, And there we can use the same mechanisms as we can use for frequency analysis, with the difference that we now have exactly synchronized lines in our spectrum. Here, for example, you see a run up, run down of a transmission over 120 seconds. This is the complete test run of such a gearbox. And you see here we see the gear mesh orders in the sideband lines, but they change in frequency, and to analyze them is quite not so easy, especially with a high resolution. If we do resampling, use the order analysis, then it's much more convenient. We exactly can see the gear mesh orders in the sideband lines, and we can do a very precise evaluation of these lines and define very precise metrics to find all the defects the customers are interested in. Yes, in order spectral analysis, we have different representations. The first one is the order sonogram, is an angle order representation or time order representation, and it gives us a general overview about the signal. Then we have an averaged order spectrum. That means we average all the spectra in this plot to one order spectrum. That gives us the average behavior of harmonics, periodics, and modulated signals over the whole measurement cycle. And on the other hand, we have an order level track. This can be calculated versus time, RPM, or another measure. And that gives us the behavior of a certain special harmonic over the time or over the RPM, so that we can find several issues that are RPM dependent, for example. Yes, then it is quite important that we really do a good synchronization of our signal. That means if we have delays in the signal processing, then this could result to a very poor order analysis. Here you see a frequency spectrum. You see that the orders are changing in frequency periodically. This is because a special load on this device under test, a special behavior. We have a periodic changing frequency. And if we do not exactly synchronize on this behavior, we see an order spectrum like this. We see some lower orders and the others start to blur and disappear. But if we really synchronize on exactly this behavior by removing all delays between Tahoe and the signal itself, we get real sharp orders that can be assessed very precisely. Yes, you see here now different spectra. The question is now, how do we have to parameterize them? And there we look at the most important parameters. This is, of course, the maximum order. That's quite easy. The sample rate has to be high enough to cover the maximum order that we are interested in. If we talk about tooth gears, it's usually 3 times the gear mesh order that we are interested in. It's the same for electric motors, for timing chains, for all this stuff. And if you know the number of teeth, then we know the maximum order. And then, of course, we have to take the revolution speed into account to set up the sample rate of our fixed frequency AD converter to a sample rate that is higher than the maximum sample rate that we have in order domain. So, for example, if we have a revolution speed of let's say 1000 RPM, and we want to analyze up to the order number 200, then we have to take a sample rate of 20, or then we have to take a bandwidth of 20 kilohertz into account. This also has influence on the sensor that we can choose to measure the signal, and on the test bench environment to be able to measure these frequencies. So that's something that can be calculated very easily. Then the other parameter that is interested is the order resolution. You see here an order spectrum coming from an IC engine. In general, it has orders in the distance of 0.5 orders. Since the slowest thing that is moving in an engine usually is the camshaft, it moves with half the frequency of the crankshaft. It has a lot of harmonics because of the gear of the valve noise. But at the end, we have only orders with a distance of 0.5 orders. And so we may think an order resolution of 1/2 is high enough to analyze these orders. Yes, an order spectrum with order resolution 1/2 looks like this. You cannot be sure if this is noise or if this is really an order. But if we increase the order resolution to a 1/16 of an order, we really see the orders and we really see the noise between the orders. And at the end, also the noise contribution of the order is quite smaller since the FFT channel is smaller. And as I explained before, the noise floor is going down. And so a higher order resolution leads to a more precise measurement. But it leads to a longer measurement time. For an order spectrum of one with a resolution of 1/16 of an order, I need 16 revolutions of the reference shaft. And if I have a revolution speed that is quite slow, then the measurement time could go up. So dealing with order resolution also has to, when we deal with the order resolution, we always have to deal with the measurement time because they are connected. And so the measurement time often limits the precision of the analysis that is possible. But this is a physical thing. This is not caused by the ANOVUS system. It is caused by the physics behind it. And if you look at the angle resolution, of course, if you have a high order resolution, then also the angle resolution goes down. And therefore, if we look for something that happens in a transient way only at special orders, it does not make sense to go into order domain. Then we have to go into angle domain. And therefore, analysis in angle domain is one important analysis method that we use in our applications. Yes, and that means if we found the right way of analysis, then we can try to define a metric. This is not always angle domain analysis or frequency or order analysis. It could be also something special like an envelope spectrum or a modulation spectrum, as you see here. This is quite suitable, as the name implies, to analyze modulations, to assess modulations that could happen. Sometimes it's more suitable than the sideband analysis. Or here we have an example of the angle synchronous envelope. This is this is a curve that we calculate for an angle domain, and it helps us to detect tooth damages. Here in our case, we analyze a manual, or no, this was a double clutch gearbox where we have 7 gears, and we want to know if on one of the tooth gears, if there's a damage on one of the tooth gears. And therefore we synchronize such an angle synchronous signal on every tooth gear that we have. And since they all rotate with different speeds, then we only see the contribution of a damage on the curve that is corresponding with the damaged gear. All these curves are generated or calculated from the same sensor. In the sensor signal, I have the transients, tick, 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 tick. They come with a certain distance. And if I do the averaging in a way that they always are on the same position of my curve, then they will be amplified by the averaging, amplified against the noise. But if the position of the peak is always different because the synchronization does not fit to this effect, then this peak disappears. Since it is on every curve that I used for averaging here, it's on a different position. And if I average them all, then I do not see the peak at all. So that's quite an illustrative way to detect damages. I synchronize on every tooth gear one of these curves. And if I have a peak, I exactly know I have one damage on tooth gear number 5. And defining a metric is also quite simple. We can put a limit here. If the peak is above the limit, then we have a defect. And we also can see the kind of defect. We see if there's only one tooth gear damaged or more teeth are damaged. This all is visible here. Yes, but this can become quite complicated if we have a lot of components in our device under test, like we have it in an automated gearbox, for example. There we have planetary gear sets that consist of a lot of tooth gears. Then we would need really a lot of these curves. That makes the setup not so easy to handle. But therefore, and also to detect bearing noises where we do not know the exact distance of the peaks, since there's slip in the bearings. Therefore, we use another technique that is something that we call angle synchronous capstrom. A capstrom is a quite old method. A capstrom is a spectrum from a spectrum. That means I calculate an FFT from an FFT. And this helps me to assess periodic peaks in the spectrum. I think you remember the slide before where I showed you the periodic recurring transient peaks, and they lead to a spectrum with many lines. Since a series of peaks in time domain will lead to a series of peaks in frequency domain and vice versa. And so if I take the frequency domain again as virtually as a time domain and calculate another FFT, then I get again a series of peaks, but the distance of the peaks is 1 divided by the distance here. And this helps me to detect defects where I do not exactly know the synchronization or the transmission ratio to my reference shaft. I only see a series of peaks with a distance that I really that is really hard to measure, since the peaks are quite small. The energy is spread over the whole spectrum, and to measure the distance is not very precise here. But if I do calculate the FFT, calculate the capstrom, the energy of all these small peaks are concentrated in only a few peaks in capstrom domain, and the position of the peak or the distance of the peaks to each other corresponds with the transmission ratio of these peaks to the reference shaft. So at the end, I only need one curve, and I can find all damages with one curve. That makes the setup quite easier. It's a little bit harder to understand, since you have to know all the transmission ratios, and then you can set up also the right metrics here, assess certain ranges of this capstrom to identify damages on several tooth gears or damages on bearings. This is then also possible if you know the transmission ratios. Therefore, any knowledge about the kinematic of the device under test is very welcome if we want to do a fault identification or metric definition. That helps us to choose the right method, to find the right components in our curves, and to set up the right metrics. Yes, but at the end, you see, those are only some examples. Time is running. We want to have some minutes for answering questions. So what you see here, what you've seen here are some examples how we use signal processing methods. We do not use them because we have them, but we use them in a way that we try to understand what effect do I have to analyze, what kind of signals do these effects emit, and what tool is the best to extract these signals from the sensor signal. Yes, and the typical methods are spectral analysis, order spectral analysis, envelope analysis, sideband analysis for modulated signals, capstral analysis for detecting damages, and modulation analysis for deeper analysis of modulation defects. And all of these methods have one in common: they have a high selectivity. That's basically one of the differences between noise and vibration test at the end of line test bench and the assessment of the emitted noise and the emitted vibration at the development. We are basically not so interested in, is it really only loud or is it less loud? We want to identify the root cause of this, why this device under test is loud. And therefore we want to separate all the different signals components from each other in a way that we really can identify this one signal that makes this contribution that shows us this part is too loud. And if we found this signal and understand how it is generated, then we are also able to identify the root cause for it. That's why we always talk about high selectivity. That's why synchronization is quite important. And that's why the setup of the system is a little bit different than if you talk about lab measurements. Yes, a metric definition is not only possible if we see a difference in the curve. Sometimes we have also cases like this that we see in the curve itself, we see no differences or no gap between good and bad. What you see on the left side is a zoom into an order spectrum. The blue lines are production lines, red lines are faulty items. And you see they are always covered by the scatter of the production. There's no position where there is a gap. But if I take this special characteristic here into account of this defect that the gear mesh line has a low energy and the sideband lines have a high energy, then I can define the metric even under those conditions that helps us to separate good from bad. In that case, it's only the relation between the level of the gear mesh line and the level of the sideband lines. If this ratio is high, then we know we have a lot of energy in the sideband lines, a lot of modulation. We have a bad condition of our tooth gear. If it's vice versa, we have a very good condition of our tooth gear. That can be expressed in such a metric. Yes, that's what I wanted to tell you up to now. Tomorrow we go one step further. Then we really extract metrics and rate them at the end of line test bench. There we have several concepts to detect known issues, detect issues that never occurred before. And this is something that I want to explain you tomorrow. And as the last session tomorrow, I will show you about 30 slides with examples of faults that we have detected or that our customers have detected on their test benches so that you get an impression what is possible with this technique. So thank you up to now. Timon, I think we will have some questions, so we could spend the last minutes to answer the questions.
Yes, we can. So the first question would be, can a novice read barcodes on the product under test, and how does it handle a retest of the product with the same serial number?
Yes, this is possible. It is a functionality of the Test Bench Connect to use such barcode scanners. If you remember, I try to open this slide again. We have here our SimCenter Novus Test Bench Connect or Test Bench Control that interfaces with the test bench, and this software also can have the functionality to read a barcode. We have modules to read, to address or access barcode scanners. And then this is used for setting the serial number and for choosing the test run number. This can be done by this is usually done by a system, by a master system, by a PLC. To really identify the test run number, we need a master system. We need a database where we know how often the certain device has been tested. We need a data set about the device, because it could happen that we have several test benches, and then we could identify, we measure the same item the second time, but we do not know if it has been tested 10 times at the neighbor test bench. And therefore, a master system, a master database that has all the information is necessary. And then these metadata are handled by Novus, and we get this information from the database.
Okay, great. Then the next question is how to differentiate the noise of the device of interest if the environmental noise is changing.
As long as the characteristics of the device under test is not changing, then we do not need to care about this. If you remember this order, for example, this order spectrum, we know the components that we are interested in only contribute the gear mesh line and the sideband lines. Everything between those lines is this external noise, and we do not care about this. So even if the noise changes between the orders, it has no impact on the orders themselves. As long as these changes are not in a way that I have a very, very strong vibration that covers all the signals from my device under test. But if it changes slightly, if you have a neighbor system running or not running, then the influence is usually quite small. But in some cases, we have to take care about this. Michael Weidner could tell us about cases where an NDT system, for example, has been installed beside a washing machine that uses ultrasonic vibrations. And nobody was aware about this, but we could clearly see the ultrasonic contribution in our spectrum. And this is, of course, something that we need to know, and then we can cut it out in the spectrum and do not care about this.
Okay, thank you. We have a question that came when you talked about the sensors and vibration sensor and laser vibrometer. What is the impact of the surface type? For example, die-cast or machined metals?
Of the laser vibrometer, if you talk about contactive sensor, then if I have a very rough surface, then of course the wear of the sensor may be affected. But the sensor has a hardened steel tip, and so it even will work under these conditions. But if there are really very rough structures there, then this could lead to signal disturbances at the accelerometer. But if you look at the laser, as long as the reflection is good enough, as long as I get enough light back in the laser, then the influence is quite small of these defects. We sometimes have an influence if there's a structure on the surface, that the structure does a kind of beam forming of the laser beam. That the laser beam is not reflected back as a kind of cylinder or as a cone, but it's reflected as a very small shape, and then we have to take care about setting up the perpendicular position of the laser. But at the end, the roughness itself has no contribution to the velocity component of the vibration, and so it's the laser is quite insensitive against it. It's more important that the reflection is high enough. So if it's a matte black surface, then it's difficult. But if it's a die cast, gray cast, steel, whatever, then we usually have no problem.
Okay, thank you. The next question is on diesel engines, for example. How do we decide upon the optimal number of sensors and their placement around the device of test to find out the faults also on complex units like 8 or 12 cylinder engines?
With AC or IC engines, after more than 500 installations in the world, we have a lot of information or a lot of experiences how to test them. And we know, for example, if it's an inline engine, then we use one sensor on the block, one sensor on the head. The sensor on the head most of the time near the timing drive. that we get this contribution. If we have a V engine, then we use one on the block and at least one on each cylinder head. And if there are turbochargers to check, then we sometimes use special microphones to test them. So the number of channels for an engine test bench is between 2 and let's say 6, not more. And the positions near the timing drive, near the oil pump, something like that.
Wherever there's space.
Yes, that's true. Of course, at the end, we are quite limited there.
Okay, then you talked about it in this presentation, but there's a question what kind of classification methods we have on the Anovis Professional.
If you are interested in that, then come back tomorrow at 11. Then we are especially talking about this.
Okay, great answer. And a short question, can the Anovis data be viewed in TestLab?
The raw data can be imported in TestLab. The measurement curves up to now, unfortunately not, but we are currently working on harmonizing the data formats in a way that we are compatible.
Okay, great. And the question that is there every time, will the webinar from yesterday be available online?
Tara, can you say something about this?
Yeah, after the it's Al, sorry. Yeah, at the end of the session week, we'll make the PDFs to the slides available. You'll get an email where you can download them, and the landing page that you registered on should turn into a on-demand site within a couple weeks. So you'll be notified of both. So. Okay.
Okay, great.
Okay.
Then, oh, there's a question just coming in right now. How many Anovis installations are applied to gearbox, transmission, axle assembly, end-of-line test stands?
Oh, I do not have all the statistics in mind. We have far more than 1,000 systems running currently in the world. We could say, let's say 3/4 of them are end-of-line test systems, very, very roughly. And they divide more or less in equal parts into engine testing, transmission testing, and testing of electric motor components, as we call them. And the steering, power steering, for example, is an electric component as well as a seat adjustment, for example. That's a little bit the impression we have. For every application, we have between hundreds of them till a few of them. And for us, if we talk about a door opener or a shift lever adjustment, this is not quite a big difference from the noise and vibration point of view.
Okay, so now there are no questions left.
Okay.
Thank you very much.
Thank you.
Thank you all. We'll see you tomorrow at 11 a.m. Eastern.
Yes, thank you also from my side, and come back please tomorrow at 11. I hope it will be interesting again. Thank you and have a nice day.
Thank you all.